Okay, so hello everyone. We're looking at Module 12 this week. Module 12 is on IP version 6 addressing. In Module 11, we've covered IPv4 addressing. We talked about subnetting. Now we're looking at IPv6. In this lesson, we will cover IPv4 issues and the need for IP version 6. We'll talk about some of the limitations that were in IPv4 and why that led up to a real need in IPv6, and thus for organizations being asked to migrate into IPv6. And then we look at IPv6 address representation, and we finish off by looking at or talking about or discussing the IPv6 address types. So those are three things I would like to cover in this lesson, in lesson number 1. Okay, so again, you have 3 lessons. This is lesson 1, lesson 2, and lesson 3. We'll cover them before the end of the week, and then you have a set of activities that you are asked to complete. Okay, so I'll attach the lecture slides. Once the video is complete, I should attach the lecture slides as well. Okay, so first things first, when we look at when we talk about IPv6 addressing, one of the things we need to understand first is that why do we need IPv6? Well, there are some obvious limitations and issues with IPv4. That's the need for IPv6. It's very clear to see this. One of the first limitations with IPv4 addresses is that it had a very small number of addresses available for use. Now, one might think that 4 billion is a lot of addresses. 4 billion theoretically addresses, IPv4 addresses that were available. Now, all these addresses had to be shared by all 5 different regional internet registries. Okay, so you can see that here we have 1, 2, 3, 4, 5 different registries, RIRs, regional internet registries, that had to share a block of addresses that came from these 4 billion addresses that were available out of IPv4. Now, at this stage in time, you can see that most of these regions have already run out of the available IPv4 addresses that they were allocated by IANA. Okay, Internet Assigned Names and Numbers Authority, or Name Numbers Authority. The IANA organization assigned block of addresses. So if we just take a closer look, if we look at say for instance our region ethnic, we come under Asia Pacific. Exhaustion date was around 2014. Okay, so which means that the last 6 years, well, 5 including this year, how is it possible that we've still managed to use IPv4? Well, because of such things as network address translation. They've allowed us to continue to use the available private IP addresses and the limited available public IP addresses. You see, the other regions have already ran out. Okay, Africa have ran out of 20 IPv4 addresses this year, 2020. Okay, so all other regions have all run out of IP addresses as well. Okay, so it's very obvious here that there is a limited number of IPv4 addresses available, and that's the reason for IPv6. So IPv6 is seen as a successor to IPv4. And if you look at IPv6, IPv6 has a much larger address space of 128 bits. If you recall, when we talked about IPv4, 32-bit address space, and that 32-bit address space is actually made up of 4 octets. Okay, those 4 octets, if you look at the 4 octets, each octet is 8 bits long. Okay, so that's 4 octets, each octet 8 bits. If you do the math, you have 8 8, 8, 16, 24, 32. Okay, so that's a total of 32 bits in an IPv4 address. When you look at the 128-bit IPv6 address space, that's 128, okay, bits. With an IPv6, there's 1, 2, 3, 4, 5, 6, 7, 8 hexstats. Okay. Now each of these hexstats is 16 bits long. Okay. So just note this down somewhere. Each hexstat is made up of 4 hex numbers. Okay. 4 hex values. One single hex value is about 4 bits long. So that's 4 by 4, that's 16 bits in one hexstat. So you have 16, 16, 16 here, another 16 here, another 16. So if you do the math and multiply 16 bits times 8 hexstats, you get 128 bit. Okay, so that's the reason why it is said that IPv6 has a much larger 128-bit address space. Okay, unlike IPv4, which is 32 bits. So given the longer address space, you can obviously see that with IPv6 that it's going to have a much larger number of addresses available. Okay, about 340 undecillion address spaces. So that's quite a lot of IPv6 addresses that are available that can cater for the whole globe. Now, apart from just having a larger address space, one of the other reasons why IPv6 was developed is to, used to address some of the limitations and disadvantages about IPv4 and look at some fixes that would be included or developed to overcome or address those challenges. Okay, for example, one is there are inherent security issues with IPv4 addresses. So IPv6 tries to address these, okay, the security issues. Now, another thing, there's some driving factors why the need to migrate into IPv6. One of that is the increasing internet population. Okay, we can see that over the last couple of years, there's been a huge growth in the use of internet all across the globe. Okay, so that's one reason. Yes, obviously a limited IPv4 address space. There are issues with network address translation. We have the popularity of IoT, and also, of course, some security issues as well with IPv4. This has given the rise for the need to for companies, organizations, and countries to start transitioning into IPv6. And it's been very slow. Transition has been happening very slowly across the globe, across the different registries, but it's still going to happen. So there's a real need for IPv6, okay, for organizations. Here's another image or figure that illustrates this clearly. I took this when I was doing a course on IPv6 through APNIC. Okay, if you look at these, as I mentioned earlier on, IANA has assigned, IANA is the Internet Assigned Numbers Authority. They've assigned blocks of addresses to each of these regions. In the next couple of slides, I'll show you what block APNIC have given to our core ISPs. For example, Telecom. I'll use Telecom as an example. What block of addresses did Telecom or did APNIC give to Telecom as a service provider within a country that's found in this region? Okay, so at this stage, it's clear that we've already ran out of IPv4 addresses. So temporarily, the short-term solution, we've been banking on NAT. Okay, network address translation has been saving us. In the long run, there's a requirement to migrate into full IPv6. At the moment, companies, organizations are still using IPv4. As I mentioned earlier on, migration, as far as I know, is happening slowly. I'm saying this from our perspective. For other regions, they are making quite huge progress in that area. Okay, so there's a real need for IPv6, and I think by now you can clearly see that one of the key drivers or factors why we have to deploy or migrate into IPv6 is because of the fact that IPv4 addresses have already been depleted. Okay, there's no more IPv4 addresses available to be given out to regional registries for use within their region. Okay, so this brings me now to share with you some stats from our end. Some of PNG's IP statistics. I took this from this country IP blocks site. If you look at the PNG example, PNG was given about 62,880. Okay, now these IP blocks block of addresses are located by the regional internet registry and are given to organizations and ISPs, and then these ISPs give them out to business houses or corporate companies, or even for other NGO organizations or large organizations to use. Okay, as long as these companies want to connect to the internet through their services, through the ISP services, they are allocated an address space from the block of addresses they've been given to by ethnic. Okay, so 62,880 was given to PNG, and out of PNG, you know for sure that PNG, there's quite a number of service providers. Some years back, there was a monopoly in that industry, and Telecom had control over, well, had the gateway for internet services. Okay, so if you look at this ASN number, okay, every organization that subscribes to telecom services, internet services, regardless of whatever WAN or internet service provision you use, you will fall under this autonomous system number, or ASN 17828. Now, the time of me taking the statistics, it was under Telecom PNG. At this stage, if you go back to this ipinfo.io and check out AS17828, you'll find that it's no longer under Telecom, it's under Data Core. Okay, now that explains, you remember some months back when the transition was made for wholesale internet service provision, transferred over to Data Core instead of Telecom. Okay, so Telecom went back into to do much of retailing and gave the wholesale business to Data Core to do. So now this AS number is under Data Core, and it's no longer Telecom. Okay, it should show Data Core. Okay, so that's basically some of the difference. The statistics in PNG. That's the block of addresses we've been given, and different internet service providers take from ethnic from that block of addresses. So if you look at Telecom took about 14,000. Okay, so that's at the time of this, when I took this information. Telecom took about 14,000 of that IP addresses and was giving it to customers or organizations or businesses that were subscribing to its services. Now there's Digicel, there's other ISPs. They also have an address spacing out of that 62,880. Now you can obviously see that this is way more than the total population of the country. Now just for a minute, think about what if every one of us were to have access to the internet. You see how this is all working out? It's possible. There's a lot more of us accessing the internet than the number given here. It's because of network address translation that we've been able to keep using the already depleted IPv4 addresses. Okay, here's some more of that statistics. I went on further to find out from that from this address allocation, 14,000 given to telecom, how much has telecom given out to organizations subscribe to its services? Okay, just for the sake of finding out for the organization I work for. Okay, this is how much we've been given. Divine Word University was given at least a block that allows it 256 addresses within that range. So which means that all our websites, web services, e-learning, intranet, we have our own website, they all use that an address from this range of addresses. Okay, so you can find your company here, the organization you work for, you can find it under here. It may even be under other ISPs as well. Okay, so this is just to give you some insight because we're talking about IPv6. It's important to know the status of IPv4 usage in our country. Now, this goes to show that although we still using IPv4, that does not mean that organizations aren't going to migrate into IPv6. There are some organizations that are slowly moving into IPv6 now. Okay, as I mentioned earlier on, this AS number 17828, the previous slide I showed you, at the time when I collected the data, it was under telecom. It's no longer that. Okay, it's now under PNG Data Co Limited. And you can see now the number of IP addresses available has gone down to 13,000. Okay, so you can already tell the rest of this, it's it's probably with telecom. Okay, telecom PNG. Okay, so let's talk about the fact that what happens when we move from IPv4 into IPv6. What's going to allow the migration to take place? Well, there are at least 3 migration techniques. What is envisioned in the future is that both IPv4 and IPv6 will coexist, and transition should take several years. Okay, maybe longer than that. Okay, so 5-10 years, we don't know, but for the Internet Engineering Task Force, they've created various protocols, so IETF, and tools to help network administrators migrate their networks to IPv6. So these migration techniques can be divided into at least 3 categories. So we have the dual stack. That's the first one. We have dual stack, and this is, by the way, this is one of the most common migration techniques. I've done a bit of background study and survey on this to just have some idea what's the transition rate or stage we are in. Most companies prefer dual stack, as we'll see in the next slide. So this is where the term dual implies devices running both IPv4 and IPv6 protocol simultaneously. Okay, so I'll show you that Windows 7, Windows 8, they support that. The previous Windows XP, you had dual stack wasn't available. You would have to configure just IPv4 only. Okay, there was no IPv6 supported. With Windows 8, you can see that Windows 10, the earlier versions of operating systems coming out, they now support dual stacking. Okay, so this is not just end devices, you also have network devices now being able to run both protocols at the same time. The next method is tunneling. Tunneling is very much like VPN tunneling. Same principle used here. You have an IPv6 packet being transported over an IPv4 network encapsulated in a tunnel. The IPv6 packet is encapsulated inside the IPv4 packet, okay, and being transported over an IPv4 network. Okay, so once it reaches an IPv6 full IPv6 network, the IPv4 packet is stripped off, and you are now left with the original IPv6 packet. Okay, so it's very much like VPN tunneling, uses the same principles. With translation, again think of NET. This time it's NET64, where we have it allows an IPv6 enabled device to communicate with an IPv4 enabled device using a translation technique similar to the traditional network address translation for IPv4. So 3 migration techniques, well, rather 3 categories of migration techniques: dual stack, tunneling, and translation. Now, do note here that tunneling and translation are for transitioning to native IPv6 and should only be used where needed. And this goes to show that when we look at the next slide, you will notice this is what most organizations use. Okay, I'll probably move this to the next slide so you can see clearly what happens here. Okay, so I took this out from AppNIC again, as I was doing some background research on this some years back. I identified what the state is like in terms of IPv6 deployment, especially in our country. I did a short poll on our Facebook group, just asking the ICT community in the country, and a couple of people responded. Almost 90% don't know what their IPv6 state of the network is, whether their network is able to deploy or support IPv6 if we were pushed to move into full IPv6. But you can see here, this is from AppNIC again, AppNIC Internet Directory. That's the source of this chart. You can see that for IPv6 deployment for our country, the blue line shows the capability. Okay, that's the percentage of users able to access online content using IPv6 within our country. Now, very interesting, if you look at the 2016 figures going up to 2017, 18, and eventually into 19. Okay, you have blue line capable. Okay, capable percentage is high here, and it's gone down. It's been varying. Okay, now red line indicates that this is preferred. They prefer dual stacking. Okay, IPv4 and IPv6. So that's the trend now. Okay, that's the trend. This indicates that in the long run, in the next 5 to 10 years, companies would prefer to have dual stack. Okay, companies would prefer to have dual stack. Oh, I don't know how I'm writing this, but they would prefer to have dual stack in the long run as we go from 2019 into 2021, 2022, and onwards. Most organizations will now look at dual stacking as a solution. They would want to have both IPv4 and IPv6 simultaneously being supported by their network. Okay, so to ensure that their networks can communicate with full IPv6 networks as well as native IPv4 networks. So that's pretty much the stage where we are in terms of IPv6. Okay, so I thought I should show you this just to give you some insight into what's happening in our region, especially in our country. So you as a network administrator or network engineer also have some idea about what we are doing or what we are covering in terms of the theory and what its practical relevance is in terms of the way the industry is changing. Okay, so that was about the limitations in IPv4 and the need for IPv6. This is where we now look at IPv6 address representation. Okay, so again, I want to remind you, IPv6 address has a total of 128 bits, and it's made up of 8 hexstats. Okay, 8 hexstats. 3, 4, 5, 6, 7, and 8. Okay, 8 hexstats. Each of those hexstats is made up of 4 hex numbers. Okay, these are 4 hex values. Okay, each hex value is about 4 bits, which means that you have 4, 8, 12, 16. So that's a total of 16 bits in one hexstat. So if you multiply 16 by 8, you end up with 128 bits. Okay, total of 128 bit in that address space. Okay, so IPv6 addresses are not case sensitive. They are written in hexadecimal. They can be either written lowercase or uppercase or both. The preferred format for writing an IPv6 address is given here. Okay, we have one hexstat colon, not like IPv4 where you have a single dot. Now we have a full colon with each hex consisting of 4 hexadecimal values. Okay, you can see an example given here. Hexstat, why I keep saying hexstat, it's the unofficial term used to refer to a segment of 16 bits. Okay, that 16 bits, in other words, is 4 hexadecimal values. So remember, IPv4 we say octet, okay, because of the 8 bits. With the 16 bits, that's where we now say hexstat, okay, hexstat. Okay, so it's an unofficial term, but it's a good term to use to remember the address structure of IPv6. Okay, in terms of how the address is represented, there are at least 2 rules. Okay, 2 rules that are used to denote an IPv6 address. The reason why we are looking at these 2 rules is because of the fact that IPv6 addresses can be quite long. You just imagine the 128-bit address. You see, if you look at this, that's the original format an IPv6 address would take. But it can be quite long. Okay, so there are 2 rules that you can use to compress. Okay, to compress a very long IPv6 address into a compressed shorter form. Okay, so rule number 1 is to omit the leading zeros. Okay, or you remove or delete the leading zeros. So for example, if you look at this 20001 0db8, we can delete the first 0, omit the leading 0. Here we can omit the 3 leading zeros and leave 1 0. There's no 0 here. We can remove this, and this. So we end up with a compressed version of that same address. Okay, so notice that this rule only applies to leading zeros, not the trailing zeros. Otherwise you're going to mess up the whole address. Okay, so we can't say this is the same as this. Okay, that's a different address. If it's just a single 2, we are assuming that in front of the 2 there are 3 zeros. Okay, we are assuming that would be the case. So you can't omit the trailing zeros. You can only omit leading zeros. Okay, so that's rule number 1. Rule number 2, double colons. Okay, rule number 2 is to do with double colons. Now again, you can see that when you have 8 hexstats, it can be a really long address, especially when you have each hexstat is just made up of zeros and zeros and zeros. Of course, we can compress this by going by rule number 1. We omit the leading zeros, leading zeros, leading zeros, leading zeros here. We omit them, and we end up with this address. Okay, now can you see that we have a consistent contiguous, okay, string of 1, 2, 3 hexstats consisting of all zeros. Okay, now we can reduce that down or further compress that by a double colon. See here, so a double colon can replace any single contiguous string. The key thing here is contiguous string, which means that if I have double zeros, 0, 0, 0 here, 0, 0, 0 here, and then 1, 1, 1, and then I can't do that twice. Okay, so that's the only exception to this rule. You can't have 2 double colons. Okay, so I can't have a double colon here, another double colon there. Again, that would mess up the whole address. Okay, so that's the only exception to this rule. Double colon can only be used once within an address. Okay, so 2 rules. Rule number 1, omit leading zeros. Rule number 2, replace any single contiguous string of zeros with double colon. Okay, just blank double colon only. Okay, so two rules, two important rules when it comes to compressing. There are a number of activities, syntax checks, check your understanding activities that you would like to do to practice this and make sense of it. Okay, so that was the rules in terms of address representation. Okay, so again, just a quick recap. IPv6 address is 128-bit long, 128-bit long. It has 8 hexstats. Each hexstat is made up of 4 hexadecimal values, or represented as 4 hexadecimal values. Each of those hexadecimal values is 4 bits, which makes one hexstat 16 bits. So 16 times 8 hexstats, we have 128-bit IPv6 address. Okay, now we just talked about two rules when it comes to representing a very long IPv6 address. Rule number 1, omit the leading zeros. Rule number 2, replace any continuous segment of or hexstat of zeros with a double colon, and the exception to the rule is never to use a double colon twice. The last section of lesson 1, and we finish off, is on IPv6 address types. Okay, so very much like IPv4, we have those three broad categories of IPv6 addresses, like unicast, multicast, and instead of a broadcast you have an anycast. Okay, so unicast, multicast, and anycast. And unicast, again, you already know what a unicast is. It's one-to-one. Multicast, used to send a single IPv6 packet to a group or to multiple devices. And with the anycast, any IPv6 unicast address can be assigned to multiple devices. Okay, so which means that you can take one single IP address and assign it to more than one device. Okay, with IPv4 address, normally you can't do that. Okay, one address can only be given to, is unique to one device, but you can send messages to all devices by using the broadcast address. Okay, so with anycast, this is any IPv6 unicast address, okay, which can be assigned to multiple devices. So it's very much like a multicast. With a packet sent to an anycast address, would normally be routed to the nearest device having that address. So unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all nodes, okay, all nodes multicast address that really gives the same result as a broadcast. Okay, so don't confuse unicast, multicast, especially anycast with broadcast. Okay, anycast is not really the same as a broadcast. Okay, and there's a feature in IPv6 all nodes multicast address that does the same thing as a broadcast. Anycast does quite a different thing than what a traditional broadcast address would do, IPv4 broadcast address would do. Okay, so those three categories of addresses are there. And with IPv6, remember in IPv4 we have the IP address, and then we have the subnet mask. Okay, remember that we used this term prefix already when we were talking about IPv4. Okay, well, that term prefix is still there. In IPv6, we hardly use the word IP subnet mask now. You will notice for most of the material you read, you will find the term prefix is used over and over and over. It does not use subnet mask, okay, which means that prefix is the accepted terminology to refer to what would normally be the subnet mask in IPv6, in IPv4. So with IPv6, you have the IP address, IPv6 address, and then you have the prefix length, which indicates what part points to the network and what part points to the host. Okay, so notice that the prefix here, this refers to the network part. Okay, and this path refers to the host ID or the interface ID. Now, do you recall that IPv6 address is 128 bits and half of 128 bit is 64? Okay, so really what you're doing here is you are halving the full IPv6 address. 1, 2, 3, 4, and then you have 1, 2, 3, 4. Okay, so the first 4 octets make up the prefix, they represent the network. The last 4 octets, hextets, they make up the interface ID or the host ID. Okay, so we'll look at where this comes in. But again, this is very important. The prefix length indicates what part points to the network and what part points to the interface ID. Okay, so do note here that strongly recommended to use a 64-bit interface ID for most networks. Okay, because of the SLAC being used in an IPv6 enabled network. SLAC is, or SLAAC is short for stateless address auto configuration. I'll explain that in the next slide, what SLAC means and what its purpose is in terms of IPv6 addresses. Okay, so this also makes subnetting easier to create and manage. Okay, so how many types of IPv6 unicast addresses? Okay, there are about 6 types of IPv6 unicast addresses. 1, 2, 3, 4, 5, 6. Okay, so remember we have unicast, multicast, anycast. When it comes to unicast, there are about 6 of them. Okay, you have a global unicast address and you have a link local address. These are 2 key addresses. Okay, don't worry about well, loopback is of course 127 in IPv4, and then we have the double colon 1/128. Okay, that's in IPv6. So anytime you want to check the functionality of the interface in IPv6, that's your link local, that's your loopback address you will have to use. Okay, but these are the 2 important addresses that we need to look at before we finish off this session. Okay, so when you look at the global unicast address, or GUA, a GUA can be thought of as a public IPv4 address. Okay, it's similar to a public IPv4 address. Now, what does that mean? Well, if you look at the global unicast, it's routable. Okay, it's routable. On the other hand, if you look at the link local address, it's non-routable. Okay, the term link refers to the segment or the subnet. Okay, so it's only specific to the subnet. Okay, it's only specific to that particular subnet. So link local addresses are similar to the private IPv4 addresses. Okay, link local addresses. Now, link local addresses are automatically assigned. Okay, now global unicast addresses, there are 2 methods. Okay, SLAC method can be used, or you can use DHCP version 6 to assign global unicast address. That's something we will cover later as we go through the rest of CCNA 2 and 3. But at this stage, there are 2 types of IPv6 unicast addresses that are important: global unicast address and a link local address. Let me show you what I mean by this. I'll just bring up okay, I'll go to Ethernet, change adapter options. Okay, so if I click on this, that's my LAN cable, unplugged LAN cable. If I go to IPv6 here, okay, hold on, go to properties. Okay, let's go use. Okay, so you can see here, hold on, let me go back here. Okay, so if we go to IPv6 address, you can see that we have an IPv6 address that you can list here. What normally happens is every time you boot up an IPv6 enabled device, it will automatically create or generate a link local address for itself. But for a global unicast address, you have to assign it one. Now do remember that global unicast address, it's routable, link local address, non-routable. But for every IPv6 enabled device, they require this address. Okay, they can function without this address, but it will be difficult for you to route packets, IPv6 packets, without a GUA, a global unicast address. Okay. The others, don't worry too much about this. Embedded IPv4, unique local, unspecified addresses. We don't need to pay too much attention at this stage. Okay, we only need to look at global unicast and link local addresses. Okay, so again, just something important about unique local addresses. When you look at link local addresses, LLAs, you will notice they normally take this address range. If you look at global unicast will have this 200 or 2001, and so on. Okay, so IPv6 unique local addresses, similarities can be drawn to private IPv4 addresses. Okay, but of course there are significant differences. They are used for local addressing within a site, or can be between limited number of sites, can be used for devices that will never need access to another network. That's the term link local. Okay, link local. Okay. Unique local addresses are not globally routed or translated to a global IPv6 address. They are non-routable. Okay, so they are similar to IPv4 private addresses. And then you have the GUAs, okay, global unicast addresses, which are routable. Okay, they are routable. They are routable on the internet. Okay, and they normally take whenever you see 200, any IPv6 address that begins with that is typically a global unicast address, and then you will see FE80 colon full colon /64. That's a link local address. Whenever you see addresses that begin off with 2000 or 2001, and those are global unicast addresses. Okay, so currently available global unicast addresses, they begin with a decimal 2 or 3, and do note that this is only 1/8 of the total available IPv6 address space, which means that there's a whole lot of addresses within that. Remember that you're just talking about the first hextet, and there's 16 bits for you to work with. It's a lot of addresses, and talking about the 2 or 3 is just the first 3 addresses. Okay, that's just the first 3 bits rather. Okay, and you still have the rest of that bits available for you to combine to come up with possible address ranges for that GUA within that first hextet. Okay, so at this stage, remember, we have an IPv628 long address. We can half it. We can have the first 64 bits to be the prefix, and we can have the rest of the 64 bits to be the unique interface ID. Well, in that interface ID, that's this. Okay, now in that prefix length, you also have what's known as the global routing prefix, and that's where you get the GUA. Okay, the rest of it, you can half that again. Okay, you half that again, so that's 64. You divide that 64 further down. Okay, further down into half, you have half of it. Excuse me. You have the subnet ID. Okay, really it will be the 16 bits there, and then you have the rest of it, which is the global routing prefix, and this is what's used to create the global unicast addresses. Okay, so later as we move into subnetting, I'll explain this further in detail, the purpose of the global routing prefix and how we can use the subnet ID to create IPv6 subnets. Okay, so with IPv6 global unicast address structures, yes, the routing prefix, that's the prefix or network portion of the address assigned by the provider. Okay, remember I mentioned that this routing prefix comes together with the global unicast address. Okay, that's required for your packets, IPv6 packets, to be routable over IPv6 over the internet. And then you have the subnet ID component. So that's the area between the global routing prefix and the interface ID. We've seen that earlier in the previous slide. And then of course you have the interface ID. Okay, so it's all shown here. Okay. Now the last one is the link local address. Now remember that the IPv6 link local addresses, they enable devices to communicate with other IPv6 devices within the same subnet or the same link. Okay, so that word link is used in place of the word subnet. So whenever you see link local, okay, that address is locally specific to that subnet only. So packets with a source or destination LLA are not routable. Every IPv6 enabled network interface must have an LLA, link local address. Okay, I mentioned it earlier on. So if it's not configured manually on the interface, devices normally automatically create one for themselves. So every time you look at the LLA address, it will, oops, why is this thing so? It will normally be in this range. The last thing I want you to do, and then we'll finish off, is you bring up command prompt, and then we'll check these two types of addresses. We'll find out the link local address if we can find one. So we'll look for a link local address and a GUA address. Okay. Okay, so let me try this. So I go open config. Okay, let's look for, yes, okay, sure enough, we found one. Can you see for my wireless adapter, I've been able to identify a link local IPv6 address, and guess what? Can you see the beginning hex step FEA0? Okay, that indicates to you that this is a link local address FEA0. Now see if you can find a global unicast address. I'll just check on your laptop as well. See if you can find one. Okay, I don't think I have one assigned here. Okay, so notice this wasn't assigned by me. This was automatically generated by the device itself, link local IPv6 address. Okay, so that's about it. We've covered three things. I'll just quickly go back to the beginning. We talked about IPv4 issues. We talked about IPv6 address representation, and then we concluded by looking at IPv6 address types. So in the address types, out of the 5-6 different types of unicast addresses, 2 addresses you need to pay attention to that are unicast addresses: the global unicast address and the link local address. Okay, so that's lesson 1. The next video I will cover lesson 2. We will talk about configuring, okay, using Slack, SLAAC, and we'll also discuss about how DHCP version 6 can be used to achieve dynamically assigning IP addresses. Okay, so thank you for taking time out, taking your lunch time out, that is, to attend this session. I'll also post this on YouTube as well. Accompanying slides for the lecture will also be added as well. Okay, have a good day.